Hello and welcome to miniature lecture number 3 for Chemistry 112 during the spring semester of 2020. In today's lesson, we'll begin a new chapter, chapter 16, and describe several new terms, including what we mean by the spontaneity of a process. This chapter, thermodynamics, to kind of put thermodynamics into context of other topics we've talked about both this semester as well as in the previous semester, is that for any chemical reaction we might be interested in, we might ask ourselves several important questions. One of which may be, what happens in a chemical reaction? So a very basic question. And that's primarily one of the main ideas of Chemistry 1 is that we can describe what happens in a chemical reaction by the chemical equation, the balanced chemical equation. Because a balanced chemical equation tells us what we start with, the reactants, and what we end up with, which are the products. And certainly also, if we know what the delta H value is for this reaction, that allows us to know whether the process is exothermic and expected to release energy in the form of heat, or endothermic and expected to absorb energy in the form of heat. This semester, though, we've talked about some other questions, and one of those is how fast does a reaction happen? That was one of the main objectives of Chapter 12, and we can measure and also predict how fast a reaction will take place by using the rate law. The last couple of chapters have been used to describe to what extent does a reversible reaction happen. And we can quantify to what extent how a reversible reaction takes place using our equilibrium constant. A large equilibrium constant means that the reaction takes place to a large extent because at equilibrium, which is where this reaction is headed, we have a fairly high concentration of products relative to the concentration of the reactants. Whereas, of course, a small value of K, a small equilibrium constant, means the reaction only occurs to a limited or a small extent, because at equilibrium, we have a low concentration of products relative to the reactants. And this chapter asks another question, which is, will the reaction happen? Will it take place? What we mean by whether a reaction will happen is whether the process is spontaneous or non-spontaneous. A process is spontaneous if it can occur without ongoing outside intervention. We may have to get the process started, but once the process gets started, it's going to be self-sustaining. A non-spontaneous process, in contrast, is a process that can only occur with ongoing outside intervention. So a non-spontaneous process won't occur unless we continually put effort and energy into that process to sort of force it to occur. A couple examples illustrate what we mean by a spontaneous process or a non-spontaneous process. A spontaneous process would be one in which we start with a brand new car, and then on its own, without us having to do anything, leave it in the garage or certainly leave it in the elements. It may take several years or even decades, but on its own, this shiny new car will eventually look like this picture and eventually rust. That's the spontaneous process. That's what's going to happen on its own. The reverse, the non-spontaneous direction, is to take that rusty car and restore it back to a shiny new looking car. Doesn't mean it can't happen, but this removal of the rust and to convert it back to a shiny new looking car is only going to happen with ongoing outside intervention. So notice, like in this example as well as all other examples, the spontaneous direction and the non-spontaneous direction of a process are always the reverse of each other. So in equilibrium, if the forward reaction is spontaneous, the reverse reaction is non-spontaneous and vice versa. A couple other examples, we have a person in what looks to be a hamster ball. Presumably this person is rolling down the hill, because rolling down the hill is the spontaneous direction of movement for this person in the hamster ball. Once the person got started, that person is going to continue to roll down the hill until they reach the bottom of the hill. To roll up the hill can happen, but it's the non-spontaneous direction. It can only happen with ongoing outside intervention. So someone literally has to be continuously pushing this ball up the hill or pulling this ball up the hill in order for the ball to roll in the non-spontaneous direction. Likewise, sort of in a similar vein, if we want to lift this heavy block, the heavy block wants to move in this direction, it wants to move towards the ground. we can lift this heavy block higher, but only with ongoing outside intervention. Notice in these two examples that the direction of spontaneous change, either rolling down the hill or the weight falling down back to the ground, is the direction towards lower potential energy. In these cases, they were gravitational potential energy, but just generally speaking, it's always towards lower potential energy. And the same thing's true with chemical reactions. A chemical process is spontaneous if it tends towards lower chemical potential energy. So all we have to do to decide whether or not a particular direction of reaction is spontaneous or not is ask ourselves, does that process lead to a lowering of chemical potential energy? With sodium chloride dissolving in water, that's a spontaneous process. It happened on its own. Process we're probably familiar with, spontaneous process we're familiar with. A process that we're not as probably familiar with is another spontaneous process that is constantly occurring on its own, is the conversion of diamond, one form of carbon, into graphite, which is another form of elemental carbon. This process is spontaneous. It is happening on its own. So it's not technically true to say that diamonds are in fact forever. There should be a disclaimer here that diamonds are only forever if we're worried about our lifetime and our children's lifetime and our grandchildren's lifetime, etc. So because even though this process does occur, it is spontaneous on its own, it fortunately occurs at a very, very, very slow rate. And this illustration of diamond converting to graphite really emphasizes the idea that there is absolutely no relationship between the spontaneity of a process, whether the process occurs on its own or not, which is a question of thermodynamics, and its speed, which is a question of kinetics. In our common vernacular, oftentimes we say something's spontaneous, a spontaneous decision to buy something or a spontaneous reaction. In our common vernacular, that normally means that it's fast or instant. But in chemistry, specifically, when we say spontaneous, it has nothing to do with how fast the reaction takes place. We can have spontaneous processes that are very fast, and we can have spontaneous processes that are very, very slow. So is chemical potential energy then the same as enthalpy? It turns out that if we look at the list of spontaneous processes, spontaneous chemical reactions, what we'll find is that most of those spontaneous processes are, in fact, exothermic, such as this one, the decomposition of hydrogen peroxide, the so-called elephant's toothpaste reaction. It is spontaneous. It happens on its own. It's very, very slow without a catalyst, but it does happen on its own. And like this one, it turns out that most exothermic reactions are spontaneous. But notice it only says most exothermic reactions, not all exothermic reactions. And the reason why most exothermic reactions are spontaneous is that because they're exothermic, because they release energy in the form of heat, as an exothermic reaction proceeds, it leads to an increase in the dispersal or the spreading out of energy in the form of heat. So an exothermic reaction is going to release energy in the form of heat into the surroundings, and that energy in the form of heat then can spread out over the space of the surroundings. Whereas endothermic processes, a lot of those are non-spontaneous, but there are some endothermic processes, such as the dissolving of sodium chloride in water, which are also spontaneous. So we have most exothermic reactions are spontaneous. Some endothermic reactions are also spontaneous, which indicates that enthalpy, this enthalpy change, having negative enthalpy change, is not the full answer as to whether or not the process is spontaneous. But, as we'll see, it is one factor that is favorable for the spontaneity of a process. A couple other examples where delta H doesn't seem to play much, if any, of a role. We have an ideal gas trapped inside flask A on the left, and flask B is vacuum, and then we have a stopcock closed currently. If we open the stopcock, what's going to happen spontaneously is that the gas molecules that are currently in flask A are going to spread out over flask A and flask B to give us this picture. That's what happens spontaneously on its own. So the gas molecules will spread out. The reverse, the non-spontaneous direction, is to start with our picture on the right and end up with the picture on the left, which is the concentration of these gas particles from flask A and flask B just into flask A. Doesn't mean it can't happen, but it means it can only happen with ongoing outside intervention. Likewise, with adding a drop of food coloring to a glass of water, that food coloring, without a stirring or doing anything to it, will eventually spread out over the volume of the solvent until it achieves a homogeneous solution. So these are spontaneous processes, even though delta H values are 0 or very, very close to 0. So is chemical potential energy the same as enthalpy? No, but as I say, it does play a role. It is a factor in determining whether or not the process is spontaneous. To get at clues as to what the other factor or factors may be to help us understand whether a process is spontaneous or not, think about this question: is the melting of ice spontaneous? Yes, no, or depends. Well, the answer is it depends, and depends specifically on the temperature. So if I take a cube of ice, put it onto a room temperature tabletop, on its own, that cube of ice will melt into liquid water. But put that same cube of ice into a low temperature freezer, and that cube of ice will not melt. So whether or not this process occurs on its own depends on the temperature of the system. So if we look at a couple other endothermic processes, such as the melting of ice, to get that last clue as to what's going to determine whether or not the process is spontaneous, we have going from solid water to liquid water, this picture to this picture. It's endothermic, it requires energy in the form of heat, but under the right conditions, it is spontaneous. In a similar vein, the vaporization of liquid water into gaseous water, also under the right conditions, is spontaneous, even though it's also endothermic. And as we've alluded to earlier, the dissolving of solid sodium chloride into its ions, aqueous sodium ions, aqueous chloride ions, is also spontaneous, even though it is endothermic. So in summary then, these last three processes, they're all endothermic, which normally would be unfavorable for spontaneity, but we know, at least in the right conditions, they are spontaneous. So what else do these three processes have in common? Well, what all these three processes have in common is that the products of these processes are more disordered. The molecules that make up the products are more in a random state than that of the reactants. Liquid molecules are more disordered, more random than solid molecules. Gaseous molecules are a lot more random or disordered than liquid molecules, and ions in aqueous state are much more disordered than those ions in the solid state. So these processes are spontaneous not because they lead to an increase in dispersal of energy. They actually lead to the opposite, a decrease in dispersal of energy. These are endothermic processes, but they're spontaneous only because they lead to an increase in dispersal of matter. The molecules in liquid state are more spread out than the molecules in the solid state, for example. And in the same way that we can measure an increase in dispersal of energy using a term called enthalpy, we can use a term called entropy, with capital S as abbreviation, to measure the dispersal of matter of a substance. So in short conclusion then for our lecture, a spontaneous process will occur on its own without ongoing outside intervention, is one that's favored by an increase in the dispersal of energy, so that's our enthalpy factor. An exothermic reaction is going to be favored over an endothermic reaction, and or an increase in the dispersal of matter, which is our entropy factor. Entropy is a new term for us, and so we'll probably spend our entirety of our next mentor lecture just talking about and diving deeper into what we mean by entropy.